Hello viewers, my name is Dr. Ajay, Associate Professor, Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. And today's topic is discussion of a tutorial question bank of Module 3, which is the very high frequency, ultra high frequency and microwave frequency. Part 2, we will see about the VHF antennas, a basic description about the VHF antennas. And this topic is related to the course Antennas, Waves and Propagation. Antennas, Waves and Propagation. So let us start our session today. The first one is the problem solving and critical thinking. Let us discuss briefly a few questions on the problem solving and critical thinking. List out the differences between the active and the passive corner reflectors and what are retro reflectors. So list out the differences between the active and the passive corner reflectors and what are retro reflectors. So here the name active and passive. So active means the device which generates a signal by itself. We call it as an active device. A passive device, it gets energy from other devices, hence the name is given as passive. So active element and passive elements, as we have seen in the Yagi antenna. So Yagi antenna, all the reflectors and the directors are regarded as the passive elements. And the active element, it generates its own signal. It generates its own signal. We are not giving, we are giving for passive element energy from other sources. Hence the name is given as passive. Now here, the differences between the active and passive corner reflectors. So here, a reflector is nothing but it gets excited from other element. It gets excited from other elements. Suppose if there is a rod, this is known as a rod reflector antenna. So this rod reflector antenna, to excite this rod reflector antenna, we need to have another antenna which we call it as the primary antenna. So for this primary antenna, this is known as this is where the radiations are originated towards the rod reflector antenna. And a reflector is a device where reflection takes place. Where reflection takes place in the intended direction. So this is about the rod reflector. If we combine two rod reflectors or if we combine two flat reflector antennas, then we call it as a corner reflector antenna. We call it as a corner reflector antenna. So you can see here. This is the corner reflector antenna. So here this is one flat reflector and this is the second flat reflector. So if we combine two flat reflector antennas, then we name it as a corner reflector antenna. And we need to excite this. So we need to excite this. We are using one extra primary antenna here. It may be a horn antenna or a dipole antenna. So the backward radiations from an antenna can be eliminated by using plain conducting sheets as reflectors. So we know that when we use a rod reflector antenna, when we transmit the signal towards the reflector antenna, some radiations are going to the backside of the rod reflector antenna. Some radiations pass from the backside of the rod reflector antenna. So to overcome this limitation, to overcome this problem, so we are going to select the flat reflector antenna, so where the backward radiations of an antenna can be eliminated. So here, this is known as the conducting sheet, and this is known as the conducting sheet. So two plain conducting sheets, when we attach at the corner, it becomes a corner reflector antenna where backward radiations can be eliminated completely. So when two flat sheets intersecting at an angle alpha are used as reflectors, then such an arrangement we call it as a corner reflector antenna. Then we call it as a corner reflector antenna. Now let us see the differences between the active and the passive corner reflector antenna. So there are two types of reflector antennas. One is the active corner reflector antenna. The other one is the passive corner reflector. Let us see the difference between the active corner reflector. So when two flat sheets intersecting at an angle alpha less than 180. Intersecting at an angle alpha is less than 180 with a driven element producing a sharp radiation pattern, then such an arrangement we call it as an active corner reflector antenna. So whenever we are going to combine two reflectors here, so for this at the center we are going to use driven element. So here we are going to use a half wave dipole antenna or a horn antenna at the center for exciting this active corner reflector antenna, so that it will provide a sharp radiation pattern. So such an arrangement we call it as a active corner reflector antenna. The opening of the corner or aperture should be in the range of 1 lambda to 2 lambda. So it is 1 lambda to 2 lambda. The passive corner reflector, when two metal sheets intersecting at an angle alpha is over 90 degrees without any driven element used, it reflects back the entire incident wave towards its source. So when two metal sheets intersecting at an angle alpha is over 90 degrees. So in the active we are using alpha less than 180. So in the passive we are using alpha is over 90 degrees without any driven element used. So it reflects back the entire incident wave towards its source. Such an arrangement we call it as a passive corner reflector antenna. So the main characteristic differences between an active and a passive corner reflectors are the absence of driven element, the angle of corner alpha, the aperture length. So the main characteristic differences between the active and passive corner reflectors are the absence of driven element, the angle of corner alpha, and the aperture length. So let us say briefly about the absence of driven element. So there is no driven element present in the passive corner reflector antenna. Hence, the spacing of the antenna from the corner and relative width of the corner with antenna is not a concern. So here, whenever we are going to design a passive corner reflector antenna, so there will be no driven element and there will be no corner reflector antenna. So there is no driven element present in the passive corner reflector. Hence, the spacing of the antenna from the corner and the relative width of the corner with antenna is not a great concern here. And similarly, we can see the angle of corner alpha. So the angle of radiation or the radiation bandwidth, radiation efficiency depends upon the angle between the two flat reflector antennas. The angle of corner in passive corner reflector should always be equal to 90 degrees. Whereas in active corner reflector, it can have any value satisfying the condition alpha less than 180 degrees. Alpha less than 180 degrees. So practically it can be alpha is 180 to the power of n, 180 degrees to the power of n, where n is any positive integers. Now the aperture length here, the passive corner reflector should have aperture length equal to several wavelengths. So whereas in active corner reflector, the aperture length should be limited up to lambda or 2 lambda. So here the passive corner reflector should have aperture length equal to many wavelengths. The corner reflector, active corner reflector aperture length must be limited to only up to lambda to or 2 lambda. The passive reflectors are used in radar applications and active reflectors are used in the wideband applications. So passive reflectors used in radar and active are used in wideband applications. A passive corner reflector is also called as a retro reflector. So a retro corner reflector is the other name given for the passive corner reflector antenna. It consists of three mutually perpendicular reflecting sheets. Mutually perpendicular reflecting sheets intersecting each other at the center, producing three-dimensional square corner reflectors. Each square corner occupies one octant, that is 5157 square degrees, and 8 square corners occupies a full sphere solid angle of 41,253 degrees square degrees. The cluster of 8 square corners together is called a retro reflector. The maximum value of reflecting area is root 3 power 2 for any direction out of total area of 4d square. So the retro reflector is used majorly in the radar applications. The metal sheets used for designing the retro reflectors will have the length up to 7 lambda and mesh holes up to the size of lambda by 2, and surface should be flat in the vicinity of lambda by 16. So these are the design specifications for retro reflectors. Distinguish between the spherical and cylindrical paraboloid. Cylindrical and spherical paraboloid. So always the radiation efficiency depends upon the design of the antenna. And how much amount of input signal frequency we are giving. So here there are two basic paraboloids. Each of these paraboloids are known as the secondary antennas. Why? Because we are going to excite these antennas with another device which is known as the horn antenna. So here in the design of any paraboloid, we are having two types of antennas. One is the primary antenna, the second one is secondary antenna. So the primary antenna is taken as a horn antenna which gives the signal to the paraboloid, and this paraboloid will reflect the energy to the intended direction. Hence the paraboloids are known as the secondary antennas. Now let us see the differences between the cylindrical and the spherical. A cylindrical paraboloid The most widely used field for this parabola is a linear dipole. In cylindrical, we use a linear dipole or linear array or slotted waveguide. A waveguide is a device where a total internal reflection takes place. It is used as a device to produce microwave frequencies, and it is closed at one end and it is open at the other end. The most widely used for this parabola is a pyramidal or a conical horn. So for a spherical, we use the pyramidal or a conical horn. So this is the shape of the paraboloid. This is the shape of the parabola spherical. On the cylindrical, it will be like this. It will be like this. This is the cylindrical paraboloid. The amplitude taper is proportional to 1 by p. The amplitude taper is proportional to 1 by r square. So it is 1 by r square and it is 1 by p for cylindrical and spherical. The focal region where incident is plane wave. So the focal region where incident plane will converge is point source focal point. So here the focal point varies with respect to the cylindrical shape or the spherical shape. So where the incident plane wave. So but in the spherical paraboloid, all the rays will be converged to one point which we call it as a focal point. But in the cylindrical paraboloid, all the rays are in parallel. That means all the rays are collimated towards one direction in the form of a plane wave. So plane waves are generated. All the plane waves or the plane rays are produced from a cylindrical paraboloid. But here convergence and divergence takes place in case of a spherical paraboloid. So no cross-polarized components are produced in the cylindrical, and cross-polarized components are produced here. So cross-polarization is possible in case of spherical. Cross-polarization is not possible in the cylindrical. It is very easy to build the cylindrical. Compared to cylindrical paraboloids, the spherical paraboloids are complex to build. And this is used for low noise applications in radio astronomy. So here the cylindrical paraboloids are used for low noise applications as radio astronomy, and also it is used only for the satellite ground based stations only. And compared to cylindrical paraboloids, these are used for radio astronomy and for small earth station applications also. We can also use these spherical paraboloids. So these are the major differences between the cylindrical and the parabolic and the spherical paraboloids. Explain the features and the radiation properties of rectangular patch antennas. So the features and radiation properties of rectangular patch antennas. So generally the microstrip antennas, the basic features of patch antenna, there will be, the first one is it will be having a ground plane here. The second one is it will be having a substrate. On the ground plane there will be one substrate. And the third one is on the substrate there is a patch, which we call it as a microstrip. And for this patch, there is a transmission line. There is a transmission line here. So these are the basic features of the patch antenna, irrespective of any shape. It may be either rectangular, it may be circular or square of any shape. So for any patch antenna, these are the basic features where required for design of the microstrip antenna. So one is the ground plane, substrate, the patch, and also the transmission line. These are known as a low profile antennas. These are known as a low profile antennas. Why? Because these are having the cost of the antenna is very less and the weight also is very less. Hence the name is given as a low profile antennas. So low profile means less cost and less weight. So whichever may be the devices which are having less cost and less weight, we call it as a low profile antennas. So a metal match is mounted on the ground level with the dielectric material, the very low size with antennas having a low radiation here. These are of different shapes: square, rectangular, triangular, elliptical. And these are the basic features. Patches become increasingly useful because they are printed directly onto circuit board. So other devices, we don't need extra hardware equipment for this. For the design of the microstrip antennas. So once we design a patch, we can directly fabricate it onto the circuit board by the process of photolithography process. Microstrip antennas are becoming very widespread within the mobile phone market. So patch antennas are low cost, have a low profile, and are easily fabricated. So this is fabricated on the circuit board by a process, we call it as a photolithography process. So the most common version of printed antenna is the microchip antenna, which consists of metallic patch above ground plane. So here the shape and the size of the patch determine the frequency of operation of the antenna. So whatever the shape or whatever the size of the patch, so the frequency of operation depends upon these two factors. So photolithography, it is used as a basic process for fabricating either the patch antenna, or we can also use this photolithography technique for IC applications also. For integrated circuit chip design also, we are going to use this photolithography, which is a phenomenon used in the VLSI design. So the basic steps involved in this photolithography are coating, developing and exposing. The pattern is here transferred into the wafer's surface layer during subsequent process. So printed antennas are inexpensive to fabricate using modern printed circuit technology. These are the basic features we are having, and applications are we are using in a space aircraft, satellite, missiles, and even no handheld mobile devices. So mostly in aeroplanes also we use on satellites. This microchip antenna is preferable. Why? Because the weight of these antennas is very less, and these can be fabricated directly at the outside of the aeroplane, at the outside surface of the aeroplane, and at the outside surface of the satellite, so that the signal will be received dynamically. So this is the basic design of the microchip antenna. The length and width are the deciding parameters which will influence on the radiation efficiency of the patch antenna. So by increasing the length and width, we can modify the bandwidth of the patch antenna. Also the substrate value, also the thickness of the substrate value also reflects on the radiation efficiency. So if we increase the thickness, let us assume the h is the thickness of the height of the substrate. If we increase the height of the substrate, the radiation efficiency, the bandwidth is increased. Again, if we increase the height, the bandwidth is increased. So there is if you still increase the height of the substrate, the bandwidth efficiency or the radiation efficiency stops. The radiation efficiency stops. So there is a limitation on the substrate of the design of the patch antenna. So the substrate thickness must not exceed 0.05 lambda. So the substrate thickness must not exceed 0.05 lambda. If the thickness of the substrate exceeds 0.05 lambda, then automatically the radiation from the patch antenna stops. The radiation from the patch antenna stops. So this is one of the design limitation of the microchip antenna. So generally these patches are manufactured by means of copper or gold. So these are the different designs of the rectangular patch and the circular patch. So here for a rectangular we are using microchip feed line. So here for a circular patch we are using the coaxial feed line or the coaxial cable. Small coaxial cable is attached to the substrate. So what are the types of feeding structures used for a microchip patch? So we are having two types of feeding techniques. One is the contacting feed, the other one is a non-contacting feed. So in the contacting feed, the RF power is fed directly to the radiating patch. So in contact means directly we are giving the RF supply, and non-contacting means we are giving the input supply indirectly way. That is, the RF power is given in the indirect way. The power is transferred to the path from the feed line through electromagnetic coupling. So through the phenomenon of electromagnetic coupling, so we are going to use the RF power to the patch. So in non-contacting feeding, we are having two types of techniques. One is aperture, the other one is a proximity coupled feed. In contacting feed, we are having center feed, offset feed, inset feed, and quarter wave line feed. In non-contacting feed, we are having the aperture and the proximity coupled feed. So center feed means for the patch, we are giving the input at the center. The transmission line is attached exactly at the center. So offset means we are going to attach the transmission line either at the corners of the patch, hence the name is given as offset feed. Inset feed, so we are getting input transmission line is attached to the inside of the patch, as we have seen here. So by making a small slot arrangement, we are going to insert the transmission line inside the patch, hence the name is given as inset feed. Quarter wave line feed. So here we are going to attach a extra transmission line to the existing transmission line, that is, it is a lambda 4/4 transmission line. So here a transmission line, for this transmission line, general transmission line is attached to the patch. Here for the quarter wave line field, we are using a lambda/4 transmission line as an input to the substrate of the patch antenna. So in coaxial feed system, we are going to use a coaxial cable by making a slot for inside the substrate. Inside the substrate here. So into inside the substrate, a coaxial cable is attached here. Here a small slot is arrangement is made. So into this slot, we are going to insert the coaxial cable into this slot, and this slot is placed for the as outer conductor. It is inserted into the substrate here. So from the substrate, a small hole is made. In that hole, a coaxial cable is inserted. So the hole, we call it as a slot here. The aperture, consists of two dielectric substrates, namely antenna dielectric substrate and feed dielectric substrate. These are separated by a ground plane. So here in non-contacting feed, we are going to make two substrates. Earlier, we are using only one substrate. Here, we are going to use two different types of substrates here. Two different types of substrates here. And these two are separated by a ground plane. So this is a ground plane. So this is epsilon R1. This is epsilon R2, two different substrates. Clear? So the metal patch is placed on the top of the antenna substrate. The patch is placed here on the top of the substrate here. So this arrangement, we call it as an aperture coupled field. Aperture coupled field here. So the transmission line is placed exactly at the center, exactly at the lower level of the dielectric substrate 1 here. So here there are two substrates here. The microstrip line is placed at the lower layer. The proximity coupled field. Two dielectric substrates are used in this technique to place the feed line, and between the two substrates and radiating patch is located on the top of the substrate here. So here two dielectric substrates are used with a different value. There are two different substrates here, and the radiating patch is placed on the top of the substrate. The patch is placed on the top of the substrate here. The applications of the microchip antenna are: the microchip antennas find several applications in wireless communication, satellite communications, require polarized radiation patterns, and also for GPS systems. So demonstrate the adaptive beam forming technique in smart antennas. The beam formation is a spatial signal processing technique coupled with multiple antennas that are adaptively phased to form the direct and concentrate the beams of the radiation pattern. So here the beam formation algorithms can be implemented in the smart antennas at both the transmitter side and receiver side to provide improved array gain, higher signal to noise ratio, and considerable reduction in co-channel interference owing to the spatial selectivity of the directional antenna array elements. So with reference to the paraboloids, explain the aperture blocking, FBD ratio, spillover, and backlog. So aperture blocking is the undesirable phenomenon associated with the quasi-gain field reflector, where the primary antenna is obstructed by the sub-reflector. So where the primary antenna is obstructed by the sub-reflector here. So in most of the cases, when we design an antenna, exactly at the focal point, we are going to place a horn antenna. So with all the rays are reflected here, and some portion of the rays are coming back and coming towards the reflection, touching the horn antenna here. So here the blocking occurs. Here the blocking is occurring here. This is known as the aperture blocking here. It is undesirable phenomenon associated with the quasi-gain field reflector, where the primary reflector is obstructed by the sub-reflector. On FBD ratio, there are the focal length to the diameter ratio. So the diameter of the aperture and the focal point. This is known as the FBD ratio. So while designing the parabolic reflector antenna, we need to take care of where to place the primary antenna. So it depends upon the three possible cases: the focal point inside the aperture, on the plane of the aperture, and beyond the open mouth of the aperture. So let us see these three possible cases here. If we place the inside the focal point, suppose this is the parabola, this is the focal point, we are going to place the horn antenna here. So in that case, a non-uniform illumination is produced by the parabolic reflector antenna. So a uniform illumination is not possible when we place the primary antenna inside the focal point. So when we place the primary antenna exactly on the focal point in the plane of aperture, a uniform illumination is possible. A plane waves are produced by the parabola after reflection. If the focal point is beyond the open mouth of the parabola, suppose this is a parabola and this is a focal point, we are going to place beyond the focal point here. Beyond the focal point. So all the rays are going beyond the open mouth of the paraboloid. So all the radiations are not focused to the source to the parabola. Some rays are not captured. Some rays are not captured here. So spillover means it is nothing but the non-captured rays from the parabolic reflector. We call it as a spillover. So whenever we design a parabolic reflected antenna, see that the spillover is very less. The spillover must be very less here. So this is about the spillover. Explain the Cassegrain mechanism in transmission mode. List out the advantages and disadvantages of Cassegrain feed system. So in Cassegrain feed system, we are going to use a subreflector antenna, and the primary source antenna is placed on the vertex of the main parabolic reflector antenna. So here we are having two types of reflectors. One is the subreflector, the other one is the main reflector. So on the main reflector vertex, we are going to place a horn antenna. The horn antenna is placed on the vertex here, and here there is a subreflector here. All the rays are going towards subreflector. They strike the surface of the subreflector here, and they again reflect back to the main reflector here. This is known as the main reflector, and this is the subreflector. So after touching the main reflector, again the rays are coming to the intended direction, to the direction that is intended. So here we are going to use two types of reflectors. So in conventional mechanism, we are going to place the horn antenna on the focal point. But here, there is a blocking is happening here. So to overcome this problem, we are going for Cassegrain mechanism. To overcome this problem, we are going for Cassegrain mechanism. So in the Cassegrain mechanism, blocking can be overcome here. So blocking can be overcome in the Cassegrain mechanism. So other technique to overcome the blocking of rays is the offset feed system also. So in offset feed system, we are going to place the horn antenna exactly at the focal point, but we are going to change the angle of incident accordingly to prevent the blocking. Accordingly to prevent the blocking here. So here the blocking is not happening here. The system we call it as offset system. So advantages are reduction of minor lobes, wastage of power is reduced, equivalent focal length is achieved, feed can be placed in any direction according to our convenience here. So with this we close our session. The references for this question bank for this problem solving critical thinking is we can refer John D. Cross, Antennas and Wave Propagation by Bakshi, and also the Kerry Prasad Antennas Base and Propagation. So let us close our session today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.